So now we have a practice question. Which one of the following statements concerning the electric dipole moment is false? So the first one is, so we're looking for a false statement. The first one is the dipole moment is a scalar quantity. We just said it is vectoral quantity, right? So we got our answer in the first try. Let's check the rest of it. Dipole moment has units of coulombs per times meters. Remember that P is Q times D, so charge is Q, has a unit of coulombs, and distance is D and has a unit of meters, so that is true. So dipole moment unit is just comes from this equation. Just find the equation Q times D and you can find the unit for that. There's no special unit for that. The dipole moment combines two intrinsic properties of an electric dipole: the distance between the charges and the amount of charge on each object. Once again, this is the equation, right? So it indeed does that because it's the charges and the the distance between charges and the amount of charge, Q and D. That's what that dipole moment is made of. Okay, so and the amount of charge and the distance between them is they are the intrinsic properties of the electric dipole. And so that is also correct. The dipole moment is directed from the negative charge toward the positive charge of the dipole. This is something you kind of need to remember. One thing that helps is it's opposite to the electric field direction, because electric field would go towards the negative and away from the positive. So it's, and they're not the same thing, of course, right? But this is a true statement. And the direction of the dipole moment is used to specify the orientation of the dipole, and that's what we're going to do, especially when we talk about torque on a dipole. Okay, so they're going to say that this is the dipole moment direction, for example, and what this means is the charge distribution is, again, it starts from negative, goes to the positive. Then I would know that this is the orientation of the dipole. If the dipole moment is this way, again, I know the charge distribution. There's negative here and positive there. Okay, so this is also a true statement. And next, so far, let's cover this. We outline how the equation for the electric field due to an electric dipole is derived from the equations for the electric field due to the individual charged particles from the dipole. So dipole, again, the word is new, but it's just simply there are 2 point charges. They have the same amount of charge but opposite signs, okay? And when you put them together, that makes a dipole. And you can treat them as particles because there's just 2 particles. So we just start from there to drive the equation. And for a single charge particle and an electric dipole, we compare the rate of which the electric field magnitude decreases with the increase in distance. So those Z's and R's. In Z was, actually, since Z was in cubed and R is in squared, cube will drop off faster. So when you look at from the same long distance, Z cube is going to be, 1 over Z cube is going to be much smaller. So we identify that dipole drops off faster, right? Hopefully those are clear, and we will do another practice question next. Which one of the following statements best describe the electric field at a distance r from the electron? The electric field is directed toward the electron and has a magnitude of k times E over r squared. Or the electric field is directed away from the electron and has a magnitude of ke over r squared. Or it is toward the electron and the magnitude is ke over r, and it is away from the electron and the magnitude is ke over r. Or it's toward the electron and it's ke squared over r. We know that from Coulomb's law we get that electric field equation, right? Using the force and F is equal to QE, we got that this is kq over r squared, and this q is in absolute value. So the electron charge is negative E, but in absolute value it's going to come out as E. So we will have ke over r squared. That's the magnitude. Anything else is not gonna be true. And the direction, if you have a negative charge, remember that the electric field lines are radially inward. And let's just do this first. Yeah, it's radially inward any direction, so it's going to be toward the electron, right? So the answer should be A. Okay, so now we are going to move on to the next section. Now the things are going to get complicated. We need calculus, integrals, derivations, and what we are going to talk about in this case, so this is for an electric field due to a line of charge. And here, first we will talk about for a uniform charge, we'll find the linear, the surface and the volume charge density. And we will find the electric field at a given point near the line by splitting the distribution up into charge elements and then summing by integration. That's what summing is, right? The electric field vectors set up at the point by each element. And we'll explain how symmetry can be used to simplify the calculations of the electric field at a point near a line of uniformly distributed charge. So far we were only able to find out the electric field due to a point charge. The rest was external electric field. We didn't know what the source was, or we didn't care. Now we want to know about the source, and we want to know the different distribution of charges. What is the electric field they create? How does it look? And what is the magnitude? So for this, we are going to we have to think about charge density. Okay, that's going to be the key thing. So it's not charge itself; it's the density of the charge. And you already know the concept of density, but you probably are more familiar with the mass density. So it's very similar, and so we're gonna look into. So we're in this case, in this section, we are gonna start with line of charge, and remember that particle is a 0D, right? There's no dimension; it's just a dot in space. And line charge is going to be the next, so linear charge. So it's going to be like 1D, and then the surface is going to be 2D, and the volume is going to be 3D. Okay, so we're going to keep increasing the dimensions. Okay, so again, this section 22.4 is all about 1D charge distribution. Let's get started. So here, electric field from continuous charge distribution. So far we have considered only zero-dimensional charge points and no extent because they were particles, just a dot again in space. So as I mentioned, charge, so far we were just really doing this, zero dimension. This is what this section is about, section 22.4, line charge. So we're going to use the linear charge density for that. And instead of using Q, we are going to define charge density lambda. Since it's one-dimensional, first of all, let's think about the mass. Mass is what? Since we are living in a three-dimensional world, right? It is the, sorry, I should say mass density. Let's clear those. And that is equal to mass over volume, right? Because it's in 3D. So just like that, charge density is going to be charge over the space it takes. If you have a line charge or linear charge density, that means it's not going to take up the volume, it's going to take up a line. It's one dimension. So you need to divide by not the volume, which is meters cube, but just simply meters, okay? So the symbol for linear charge density is lambda, so we are introducing more Greek letters. There are a lot more coming in this class. And lambda is, as you can see from the unit is coulombs per meter, so lambda is going to be Q over L. Okay, and for two dimension, we have the surface charge density. And again, this is going to be if the charge is given on a surface. It could be a plate, for example. So what we need to do next is then we need to use the density, charge density of sigma. Okay, so we always use this for surface, and that what that means is the charge over area. So it's going to be Q over A. Since it's that, Q is coulombs, area is meters squared, so it's coulombs per meter squared. Another one is in 3-dimension, volume charge density, and it is represented by rho. This is rho. Most of you will say P. It's okay, it's just a Greek letter, okay? It looks like P, I know that, tilted P, but it is really rho. When I draw it, I do it this way, okay? And it is the charge divided by volume. That is a V. Okay, volume, and again, volume is meters cube, so you have coulombs per meters cube. This is what's coming in this chapter, and right now we are in line charge, so we are going to focus on this one.